Okay, and today we have two topics. The first one is to start the discussion on conservation of angular impulse and momentum. And we're gonna to discuss one example, and we will revisit example 28, which is the problem regarding a punchback. And after the class, I think that we have interesting discussion on that punchback problem. Some students wonder that how come at the moment when a force is applied to the punchback, how come the punchback doesn't move? Now, I think that revisiting example 28 can certainly clarify some possible confusions on that. And the second topic we will talk about today is eccentric impact. And the formulation is provided on my notes from page 55 to 56. But I will first start with relating whatever we talk about in the linear impact. Then we're going to put this eccentric impact to the framework of dynamics. So you will know where it stands, and you will know that everything we talk about here is no different from everything we talked about before. It's all part of a system. And the key is just to realize that how this system is formed and also how the system is structured. Conservation of linear impulse and momentum, or you can also call it principle of linear impulse or momentum. Now, some of you may wonder that how do we differentiate these two? When you consider everything, that means you consider linear impulse or angular impulse along with linear momentum and angular momentum. That formulation by itself is what we call principle of impulse and momentum in the linear form or the angular form. But when you apply it to certain problems, in some cases, there is no momentum, which usually means that it is unconstrained motion. When an object is in unconstrained motion, linear impulse or angular impulse should be preserved before and after motion. So that's when we use the word conservation of linear impulse and momentum, or we say conservation of angular impulse and momentum. So start with the formulation first. As you know that conservation of linear impulse and momentum, it all began from this. F equals m times dv dt. Of course, when we apply it to force equilibrium, we just say that this is F equals ma. Now, of course, always remember that the force and A in general should be in the vector form. Now, by moving dt from the left-hand side, from the right-hand side to the left-hand side, and you integrate both sides of the equation, you have integral of f dt equals m dv. That's what we have. And of course, we will not be able to evaluate these two integrals without providing the limits. So for the left-hand side, you say from T1 to T2, the right-hand side from V1 to V2. For the entire system, you always want to consider all different kind of forces, which is why we usually put this summation on the left-hand side. Now, this will lead to the familiar form of what we call principle of linear impulse and momentum, which is just summation of f dt integrated from T1 to T2 equals m times V2 minus m times V1. So this is what we have. And this whole thing is we call conservation of principle of linear impulse and momentum. Linear impulse is this part. The left-hand side is what we call linear impulse, denoted by capital I. Again, you know we use capital I for different purposes. What do we use capital I for? In dynamics, What do we use it for? All right. So this is the thing that, what do we use capital I for? Anybody? We use capital I for mass moment of inertia, remember? Right? We also use capital I for mass moment of inertia. Now, how do you distinguish these two? When you have a subscript, it's capital I, but the subscript is for 1 to 2. That means this is linear impulse. And if you use capital I, it's a single subscript. And this subscript is usually denoted by the point, such as I naught. And that means this is the mass moment of inertia at a certain point. Now remember, mass moment of inertia also is directional, which means besides the point that you specify, you also have to specify the direction, correct? So in addition to one subscript, usually you're going to say that this is the mass moment of inertia along the x-axis. So sometimes you can say this is another subscript is needed. And that's how we distinguish these two. So to describe mass moment of inertia, you have to specify the point. You also have to specify the direction. But for linear impulse, you have to specify 2 time instances. This one here is linear impulse. And this one here is mass moment of inertia. They all denoted by capital I, but by the ways that they are written, they have different styles for the subscript. You can tell which one is which. Okay? Just don't confuse one with another. Now this is the linear form. What is the angular form? The angular form is very simple. Now of course, finish the definition. The linear impulse is the left-hand side and the right-hand side. These two terms individually are what we call linear momentum. Now, the formulation I talked about before, so this is just a very, very quick review. Suppose I cross both sides. So the same formulation here, if I just apply this part to both sides from the original equation, and then this will give us the angular form of impulse and momentum. So we're going to have m dt from t1 to t2 must be summation equals to what? So here the dt will be moved from the right hand side to the left hand side to become this. Now whatever we have here on the right hand side of the equation becomes r cross m times dv. Now because mass is constant, so you can take the mass out of the equation. Mass is always going to be the same. So this is going to be m times r cross v, which you can say that r cross v2, because it's going to be v1 to v2, minus r cross v1. It's going to be like this, right? Mm-hmm. It's going to be like this, correct? So you look at this formulation, you're back to here. Okay. Now, the product we have in the moment part is going to be what? And this part actually is written as mass moment of inertia. Of course, when we specify the moment, you have to specify the point. So we're going to say that this is actually at the center of gravity to make everything simpler. So the right-hand side is written as I omega 2 minus Ig omega 2 minus Ig omega 1. Now, the subscript must be consistent. So if you use a different point rather than the center of gravity, you have to choose the mass moment of inertia at different points. So